Hi there. So in this video, I want to talk about the radial Schrodinger equation that in a lot of the research that we do, we end up solving. By radial, I mean you usually have a three-dimensional system, and what we're going to end up with is just equations that depend on r, the radial coordinate. But we always start with the Schrodinger equation, and this can appear differently depending on the particular problem that you're trying to solve. But let's go ahead and in this video, we'll just derive or look at how the radial equation is derived. Later videos, we'll look at how to solve them and apply them for various situations. So first of all, we're going to talk about the radial equations, and we're talking about solving the Schrodinger equation in 3 dimensions, right? And so you could write the Schrodinger equation in Cartesian x, y, z coordinates, but if you have a potential energy function, which I write as u of r right here, that is spherically symmetric, it's natural to use the spherical polar coordinate system. And you can also use this for potential functions that are not spherically symmetric, and we can look at that later on. But we'll deal with the spherically symmetric case for now. So just to recall, maybe you've seen this spherical coordinate system before. I defined my right-handed x, y, z coordinate system here. And my theta angle is measured from the z-axis. It goes down. R is the distance from the origin to the point that I'm interested in. So my 3 variables are r, theta, and phi. Theta is sometimes called the azimuthal angle. It is measured from the z-axis, and it goes from 0 to pi, right? It just goes from the positive z to the negative z, or from 0 to 180 degrees. The phi angle, sorry, I got it mixed up. Theta is the polar angle, phi is the azimuthal angle. But the phi goes all the way around. It starts at x and goes 360 degrees around the z-axis. Okay. But we have this point described by those 3 variables. One thing to point out, if you look in a mathematics textbook, they will often switch the phi and the theta. I don't know why that is, but math and physics switch the variables in that case. Now you can relate these spherical coordinates to x, y, and z, and you can make coordinate transformations. In fact, you can write derivatives, gradients in the x, y, z coordinate. You can write them in spherical. So there's a lot of, I guess you'd say, vector calculus that can be done. But the thing that we're interested in for the Schrodinger equation is this kinetic energy term, which has the gradient squared. I'm not going to go through the detail in this video of how this is obtained, but it turns out when you make the coordinate transformation, you get this expression for the gradient squared of a function psi that depends on r, theta, and phi. Right? And we can think of this as an operator. We could kind of say that all of this stuff is operating on the function, taking the derivatives, multiplying by the r's, the sine of thetas, and things like that. And if we do that, we could look at the angular part. Now there's a 1 over r squared here, but I'm going to talk about an angular operator, and I'm going to call it L squared, and it's just the sine, theta, phi parts of the equation here. And it turns out that this is related to the angular momentum. And maybe we can go into more detail in that relation later. We're going to talk about the mathematics of it a little bit here. But what I can then do is if I define this L squared, I can rewrite my Schrodinger equation as sort of a radial and r operator and an angular operator acting on the wave function. Then you still have your potential energy, and you've got your energy, right? The total energy of the system here. Now, what we can do first, what we're ultimately trying to do is to, in some cases, like a bound state case similar to the infinite square well, you want to find the eigenenergies and the eigenfunctions, right? The solutions to the eigenvalue problem, which would give me the bound state energies, say, of a hydrogen atom or something like that. The other situation that we will look at is we're trying to solve U for a continuum or continuous value of energies. What that might describe is a beam of particles, electrons maybe, with a certain kinetic energy that are far away from the potential, where the potential goes to zero, and then they come in and scatter. Now, both of these problems are described by the same equation, but what's different is the boundary conditions that we apply. And again, we will get to boundary conditions later on. I just want to rewrite this equation by sort of, in a way, separating out the angular and the radial r variable. So the way that we can do that is to just look at the angular part of this, right? We're going to just look at the operator L squared acting on the angular part of the whole function. Now, it turns out that if you take this operator, you can solve the eigenvalue equation, which would be like the operator squared times a function equals a constant times a function. And you get solutions to that that are called spherical harmonics. They're denoted by this YLM. They are particular functions that are solutions to this equation. And remember, the L squared is given by this. So we can talk later and write down particular solutions of this, but we also get this eigenvalue, which is L times L plus 1. Now, if you've ever studied chemistry, you may know that the atoms around, or the electrons around an atom exist in certain shells, and one of the quantum numbers that describes the shell is this angular momentum L quantum number. Also, M is another quantum number. It's called the magnetic quantum number that only really comes into play necessarily when you have a magnetic field, for example, applied to your atom. But this is where those quantum numbers come from. They come from solving the Schrodinger equation. Okay, so just to summarize here, I have split up the operator del squared into an angular and a radial part, and I'm writing down the solution to the angular part. And again, in the book, in any quantum physics book, they will go through the details of solving this, and they will write down the spherical harmonics. Again, maybe we can do that later, but these are my solutions to the angular part, and they have constants, L times L plus 1, where L is 0, it's a positive integer, or 0, 0, 1, 2, 3, 4, right? So these are the only possible solutions there. So we got the spherical harmonics. Now we want to go and kind of use them to get rid of the angular part and end up with just an equation for the radial part of the psi wave function, since we know what the angular part is. Okay, so let's go ahead and look at how one way that can be done. And it is kind of a separation of variables, but one thing that happens in quantum physics, when you solve an eigenvalue problem, it turns out you can expand any other function in terms of those eigenfunctions. So I have a function psi that depends on r, theta, and phi. I can expand that function in terms of an infinite sum of spherical harmonics. Now I do get a radial part that is multiplying that function. It's kind of like my constant, right? If I did a Fourier series, these would be my constants that I need to choose to give me this function. Now, you could also have within this a normalization constant if you're doing a bound state problem, things like that. But the point is that I am writing the solution as a sum of known functions. Mathematically, you would say this is a complete set of functions. It can describe any function in that three-dimensional space. But what I will do now is I'll plug this in to my Schrodinger equation, equation 4 on the previous page. Let me just show that real quick. So this equation for the Schrodinger equation, I plug it in. And one reason I chose U of L of R over R is because it simplifies things when you do all the derivatives. What you end up with is just a simple second derivative of U. Now the U sub L's, each function will depend on the value of L. It turns out not to depend on M when it's spherically symmetric. But I get this part, but I also get, right, an L times L plus 1 part, which came from the L squared operator that appeared in equation 4. I get my U sub L, the R ends up being canceling out if you work through it. And then I get my potential energy function times UL of R, and I get all of that multiplied by my spherical harmonic. On the right-hand side, I get the total energy times UL of R YLM. Now, you could say, well, now I can just cancel out the YLMs, right? And I guess that would work. But generally, one thing that you can do with these functions that are solutions to the eigenvalue problems is realize that they are what we call orthonormal. And I'm going to use that. I'm going to multiply on the left side of both sides of this equation by YLM star. Take the complex conjugate L prime, M prime. So they may have different values of L and M. I multiply, and now one thing I really should have put here, there should be a sum, right? I actually have a sum over L and M. I forgot to include my sum here. So I can't really divide, it's a sum of terms. So I should have a sum Lm. So when I multiply on the left by this complex conjugate function, I then integrate over the angular part of the spherical space, sometimes called the solid angle, sine theta, d phi. Turns out that the YLMs are orthonormal. And what I mean by that is when you take the integral of two functions, YLM, its complex conjugate, and its self, it's equal to 1 if all the L prime, M primes are equal to L and M, or it's equal to 0 if they're not equivalent, right? So what I mean by this delta L prime, this sometimes is called a Kronecker delta. It just means it's 1 if L equals L prime and M equals M prime. And it's 0 if L is not equal to L prime or M is not equal to M prime. Everything has to be the same, and if it is, it's normalized, so it's equal to 1. So what you will see when you multiply and integrate, it will pick out a particular value of L and M, right? And so it depends on whatever every value you actually multiply by, it'll pick out whatever particular value. Now this is not a procedure that's often done. Usually you do separation of variables in this case, which end up with the same results. You obtain these radial equations. I basically canceled out the YLM. And then I'm going to do a little more simplification. I'm going to define a constant k squared equal to 2me over h bar squared. V of r is equal to m over h bar squared u of r, right? So it's just a redefinition of the potential function. And if I were to use my atomic units, where the mass of the electron is 1 and h bar is 1, right? They would just be equal. But ultimately, if I work through all this, I get my radial set of equations. So these are the equations we're actually going to solve. They're just a single, one-dimensional ordinary differential equation that we will end up solving numerically. Now, I kind of went through that quickly. Hopefully it makes some sense, but I wanted to give you a feeling of where that radial equation comes from. Basically, it comes from starting from the Schrodinger equation, doing some math, right? And basically sort of integrating out or separating out the angular variables. So the next videos, we can talk about a couple of things. We could talk about solving this equation, for example, for the hydrogen atom, which would have a Coulomb potential. That would be our potential. Or we could use other potentials, but the potential that we choose describes the target or the actual system that the electron is moving around in. When we do a scattering problem, it will describe the interaction between the electron and the target. We can do similar things and get similar radial equations for positron scattering and for positronium scattering, right? So a lot of the stuff that we end up having to solve are radial equations like this. So I'm going to stop there. Hopefully it gives you a little bit of an idea of where the radial equation comes from.